Sorry, Isaac, got started without you, but
So on number 5A, is that related? Is that where the complex numbers is supposed to go?
yeah, well, actually, Alex, seriously, do I know what 5A is?
Okay. Although hyperbolic functions do not seem like they should be related to trig functions, they are mathematically related by
That's numbers. Yes. So yes, there's your journal answers. They're combinations of e to the x and e to the negative x. I'm only going to have you, as far as knowing the e to the x part, I'm only going to learn sine and cosine. We aren't going to do the other 4 trig functions in that depth. So to give you an example of this, with hyperbolic functions, you have hyperbolic sine. They write it with sine with an h on the end. That means hyperbolic sine. And hyperbolic sine is actually, by definition, e to the x minus e to the negative x over 2. I don't know if that may be on the journal. I'd have thought I would have put it there, but I can't tell you I'm positive I did it. Okay. Hyperbolic cosine is almost the same thing, except it's got a plus in the middle.
Is that the definition of?
Yeah, that's the definition of hyperbolic sine and cosine. Yes, that is what they are. That should be hyperbolic sine of x. Thank you. Do I have an iffy way? Sine subtracted, cosine's added. No, I don't have a good way to remember that. But I'm not making you learn the other 4 as far as in terms of ease. We're going to actually learn how to do derivatives and integrate hyperbolic functions, which is almost the same thing as doing trig functions. There's very little difference. Okay, so they might ask you to find the hyperbolic sine of the natural log of 3. So what do they want you to do? Yeah. Yes, exactly. And then, okay, simplify that. What's e to the natural log of 3?
3 plus 3 over 2.
I won't buy that. I'll buy the first 3. You can't cancel when there's a negative in front, so you can't have any number in front of a log and have them cancel. Where do you put numbers in front of logs? Yes, it goes back and becomes the power. That's like -1. So it's going to come back here. We're going to take that -1, move it back as 3 to the -1 power. So it's actually 3 minus. You didn't change sign, so it's still minus. But yes, that would be minus 1/3 over 2. Okay, 9/3 minus 1/3 is 8/3 times by half when I flip that over, which is 4/3. And today you've evaluated a hyperbolic sine.
What does that mean?
Okay, it's the value of that function at the natural log of 3. So it is. Now, the interesting part of these is what the graphs look like. And I need you to actually, hopefully you've got a textbook. Do we have a textbook or not? Anybody have a book?
I got it.
So I don't want you to run for them. Not worth that trouble. Dude, come down. Well, that's all the... There are the graphs. Okay. Which one is most famous and most important in engineering? Hyperbolic cosine. Why? It looks like it's parabola. It is not a parabola. It's e to the x plus e to the negative x over 2. But it's very much like a parabola, but it's even better than a parabola. It is what we call a catenary. And a catenary, and let me spell that for you. Hyperbolic cosine here. A catenary is the shape you get if you take a string and dangle it between 2 pins. When you string decorations in little loops across, that natural loop you get, those aren't parabolas, those are catenaries. Catenary. Okay, a catenary is structurally extremely strong and supportive. Catenaries just provide great structure to things. So when you see, well, for example, the Golden Gate Bridge with those 2 big towers, and they got those big cables. When you see a bridge doing that, those are catenaries. Those aren't parabolas.
So when you add,
because they make it structurally strong. Sometimes you see those arcs underneath the bridge supporting the base of the bridge, all catenary. The arch in St. Louis is catenary. Next class I'll pull out my T-shirt that has the whole formulas on it for the whole arch, and it's all hyperbolic functions.
When you say it's general equation, do you want hyperbolic cosine, or do you want the EAX plus?
I'm good with hyperbolic cosine. It's fine. Okay, so hyperbolic cosine is probably, not to say that some of those other graphs aren't also important, but that's, for engineering purposes, that's the one that's got a lot of structure to it that can really provide support. I mean, think about it. The St. Louis Arch has been there since sometime in the 1960s now. It's got to have been through some serious winds. Who knows if there's any tornado force winds. It's very sound. Does it sway? Yes, a little, but still structurally very sound. If you look at tons of bridges, they got catenaries all over them. Very, very popular design method. So that's why we care about hyperbolic functions. Okay, all I want you to learn to do with these is learn how to do derivatives of them and integrate them. The good news is the derivatives are almost identical to the trig functions you know. The only thing that switches here is some negative signs. So I'm sure somewhere on that journal I asked you to list the derivatives of the hyperbolic function.
Yep, that very last one.
Okay, so the derivative of hyperbolic sine, anybody want to guess?
Hyperbolic cosine.
Hyperbolic cosine. And the derivative of hyperbolic cosine? Close. It's positine. It's one of the ones that changes. It does not have a negative on it. Okie dokie. So those two kind of pair up. Hyperbolic tangent. You already know it. Derivative of tangent. Secant squared. So hyperbolic secant, however, squared.
So you don't put that square between.
Nope. Hyperbolic secant is all one term, then you square it. And so therefore, if I want to do cotangent, it's going to be, the big question, is it negative? And yeah, this one is. Negative hyperbolic cosecant squared. Okay. The other change comes with secant. It's cosine and secant that switch. Normally secant is secant tangent. So this stays hyperbolic secant times hyperbolic tangent, but there's a negative on it. Cosecant, however, is also still negative. They're both negative. So the only ones that switched on here were cosine and secant. They switched signs compared to what we normally work with. Otherwise, it's identically what you know. One other little formula that's sometimes helpful. You remember good old sine squared plus cosine squared equals 1? Good old fundamental identity number 6 that we live and die by? Well, in the land of hyperbolics, it's subtracted and it equals 1. Not added. Yeah. And once again, not going into all the details. I mean, seriously, hyperbolics get one section of a calc book. One little tiny section. I think if they want you to know more, they let the engineers get more serious about it. So you're going to know they exist. Okay, your challenge of the day is, can you do a derivative? And actually, this is excellent review time. Do you remember how to do basic derivatives when they contain quantities in them? Chain rule. Been a while since we did chain rule. Okay, so normal chain rule says you do what? Derive the outermost thing. So okay, yes, it's hyperbolic sine of what? The entire quantity is still inside it.
Move that half times sine.
So then I have to do the derivative of the inside, which this quantity would be to the half power, so I would really have 1/2. Write it all down to the what? Am I done? Derivative of the inside of that root was a negative 2x. And then they are going to have you clean it up a little bit. There's a touch we could cancel here. Yeah, the 2's are gone. And then so they'll just clean it up and put it in a fraction. Since it's a negative power, they'll drop that root back to the bottom and put an x times the hyperbolic sine with a negative out front, sorry. And call that good. They will not rationalize something like that. They'll leave it at the bottom. Woo! That's doing derivatives. Is that amazing? And seriously, this is a review of product and quotient rules, the chain rules, that kind of stuff. You just have to use these derivatives. Remember to change two negative signs, and it's the same thing you've been doing all year. Not a big surprise. Okay. On the other hand, I'd like to get that on the screen if I could. Okay, I also have you doing some relatively simple little integrations. So I might have you integrate me a hyperbolic sine to the 7th of x times a hyperbolic cosine of x. Okay, how do you do integration? Why do I have to substitute that? It's a quantity to the power. You got to sine to the 7th power. We can't do that. Okay, so what am I subbing for? The hyperbolic sine. Because I'm okay with having u to the 7th. And remember, you have to think ahead. If I do the derivative of that, will it cancel this cosine that I don't want?
Yes, it will.
Yeah. So remember, think ahead. Am I going to get a derivative that will cancel? So, yeah, derivative of hyperbolic sine is just hyperbolic cosine. And so, if I sub in a du over hyperbolic cosine, those cancel. Sayonara. Okay. This is where I had trouble. What shocked me when you're integrating on your area volume test. How do you integrate that? I just had tons of people who got this far or whatever, or got it simplified and then to FOIL it or whatever, and you never integrated it at all. Like, you have to integrate somewhere. Yes, u to the 8th over 8. Of course, plus c, since we aren't doing definite intervals here. And then sub in our hyperbolic sine now to the 8th power. So, not looking for rocket science on these. Good basic practice. Just need you to get a little bit familiar with the hyperbolics in case many of you suddenly decide you want to be civil engineers. I'm sure there are some other uses for these but out there in places, but that's the biggie. Hyperbolic functions. We're calling it a day. Am I doing all that? Oh, I should stop it now too. That would be a great